So far we have covered the 2D rigid body motion, which is the fixed axis rotation, and the general plane motion. For the rectilinear and curvilinear translation, we can model the rigid body as a particle. This is because the radius of B with respect to A is remain the same during the rectilinear motion and the curvilinear motion. Where you can see the relative vector here are remain the same all the time. For example, you draw 2 points randomly on this rigid body and then form the relative displacement and observe the movement of the displacement vector. So if you see the vector doesn't change the direction as well as the length, then we are saying the relative displacement are equally same during the motion. If the relative displacement is remain the same during the motion, then we can have the velocity and acceleration equally same at all the points in the rigid body here. Therefore, we can simplify this problem into a particle motion. We cannot represent the rigid body by using the particle. This is because when you form 2 points on this rigid body and observe the relative vector during the motion, the relative vector is rotate with respect to the center here. Then we know that the rigid body is doing the fixed axis rotation. Let's check the motion for the last case here. So we have a root 1, root 2, and the piston head here 3. Let's draw the relative vector for the point 3 here. It is moved in a straight line. Therefore, we can model the piston head here using the particle as it follows the rectilinear translation. Let's check the relative vector at root 1. So during the motion, the relative vector just rotates with respect to the center here. Therefore, this is the fixed axis rotation, and we need to model this by using the rigid body. Let's check the motion for the root 2. Initially, you have the relative vector in this direction. When the root 2 rotates to the center here, then the piston will be pushed to the maximum position. Then the relative vector at this position will change to this position. Let's zoom in the relative vector for these 2 positions. So you have the first relative vector here. This is the next relative vector. You can see that the point A here is doing translation. Then you move the relative vector to this position. To reach the final motion, point B here is rotate with respect to A, and therefore you obtain the final position. Since the relative displacement RB with respect to A is doing the translation plus the rotation, so in this case we have the general plane motion for the root 2. In this example, it shows that for a mechanical system, it might involve several types of motion. So you need to master this motion in order to identify which formula to be applied. You should master the technique to identify the motion by using the relative vector that I showed in this example. So we know that the root 2 here is doing the general plane motion. Therefore, we cannot treat it as a particle. For the general plane motion, if the relative vector consists of translation plus rotation, then we are saying this rigid body is doing the general plane motion. Bear in your mind, particle does not undergo rotation motion. Only the rigid body can undergo the rotation motion. If you have these 2 types of motion, then the relative vector will be different, and when you perform the differentiation to obtain the velocity and acceleration, you will obtain non-zero result. For example, to find the motion for point B, that is rotate with respect to the center here, which is point A, we can use this formula. The tangential velocity due to the rotation here is equal to this formula, omega cross RB/A, where the omega is the angular velocity. RB/A is the vector here. You have two acceleration components due to the rotation here. First component is the tangential direction here, which is equal to omega dot, or the angular acceleration, multiplied with the relative displacement. The second acceleration component is acting toward the center, which is equal to the normal acceleration here. Once you find the tangential velocity, you can substitute inside this formula to obtain the omega cross v. So this is the normal acceleration. Root 1 here is doing the fixed axis rotation. Let's say you have point A here and point B here. Then we can use the same formula to obtain the velocity and acceleration result at point B. The second root here is doing the general plane motion, which consists of the translation and the rotation. Let's label the point here to be B and C. To find the velocity at C here, then you have the velocity at B plus the tangential velocity due to the rotation with respect to B here. So the relative displacement here is equal to C slash B. And to find the acceleration at point C here is equal to the translation at point B plus the rotation at point C with respect to B, which give you these two terms where you have the R C with respect to B. The omega that we use here is the omega for the second root. So you need to find the omega for the second root, and it's different with the omega for the first root. Similarly, the angular acceleration at root 1 is different with the angular acceleration in root 2 here. In this example, you have a mechanical system which consists of a root AB, root BC, and the C is allowed to move in a linear direction. The linear velocity and linear acceleration of the object C here are given by 2 meter per second and 10 meter per second square respectively. The velocity and acceleration are acting in different directions, therefore this object C is in deceleration, which means the velocity at point C here will be reduced in the next moment. The length for the root BC and root AC are provided. The boundary condition for the point A here can be shown in this picture, which is the pin support. The pin support constrains the motion of root AB, which is allowed to rotate in one direction only. In this example, you are required to find the angular velocity and acceleration of the root BC here at this instant. First of all, let's assign the coordinate for the xy axis here. Then you can convert all the scalar quantity here to be the vector quantity. C at point C is equal to 2 in the positive x direction. Therefore, the velocity vector is equal to 2i. Then the acceleration at point C is equal to negative 10i, because the direction is in negative x direction. Since you have 45 degree here, then the angle here will be 45 degree as well. Your BC vector, which is the displacement C with respect to B, will be equal to the displacement of the BC in the x direction plus the displacement at the BC at the y direction. Don't forget the slash here. This indicates the vector is from B to C. So your relative displacement is equal to 0.4 cos 45 in the x direction plus 0.4 sine 45 degree in the z direction. By using the same approach, you can find the relative displacement RB with respect to A here equal to the x component in the negative x direction. Therefore, you have negative I. For the magnitude, you have 0.6 cos 60. Plus the y component here in the y direction. Therefore, you have j. So the magnitude is 0.6 sin 60. Since the angular velocity at root AB is not provided, therefore we just assume it to be omega AB in the positive k direction. So you have the rotation in counterclockwise with respect to z direction. Therefore, we have positive k. The angular velocity at root BC is not provided as well. Therefore, we just assume it rotates in the counterclockwise, which gives you the positive k direction. So the omega at root BC is equal to the magnitude multiplied with the direction. Later, if you obtain the result in positive, let's say 5k, then it agrees with our assumption, so your rotation is in counterclockwise. If you obtain the result in negative later, then it means that our assumption is wrong. Based on this result, the actual rotation will be in clockwise direction. You must be able to identify the motion at these three components here. If you are not sure the motion, draw the relative displacement for the rigid body that you want to investigate the motion. So you have RB slash A here. Due to the pin support here, which is the center axis of the rotation. So you have the half B moving in a circle. When you check your relative displacement, the direction change, and point B is rotate with respect to A. Therefore, the root AB is performing the fixed axis rotation. Let's continue with the root BC. Draw the relative displacement for the RB with respect to C here. At this moment, the root BC is changed to this position. If you overlay these two vectors together, so this is the initial position, this is the later position. We see the root BC is doing the translation plus the rotation. With that, we know that root BC is performing the general plane motion, which consists the translation plus the rotation. Finally, let's look at the motion for the object C here. So after it moves to this position, then your object C will move to here as well. Then you draw the relative displacement on the object C, and the relative vector here is translated in a linear motion. Therefore, we know that this is rectilinear motion. In this case, we can assume all the points here in the object C to be a particle. This is because the velocity and acceleration at all the points here will be the same. The velocity and acceleration at point C are provided here, and we don't know the acceleration and velocity at point B here. In general, we can use these two equations to find the velocity and acceleration for the general plane motion case and the fixed axis rotation case. Let's consider the motion for the root AB here first. To find the velocity at point B here, you need the velocity A as well as the angular velocity and the relative displacement, which is from A to B. For the fixed axis rotation, where you have the point B rotate with respect to A here, since the A is the center of rotation, therefore there is no velocity and acceleration at this point. So the velocity here will be equal to 0. because there is no translation here. We have obtained the RB/A here previously, so you can substitute the vector inside. Then this is unknown, and we assume this to be omega BA in the positive k direction. So you just substitute this inside the vector. So you obtain the first equation. Then you continue to form the second equation for the acceleration at point B here. So you have the translation component and the rotation component. For the translation component, you need the acceleration at point A here. So at this point, acceleration is equal to 0 because this is the center of rotation. So this one can be cancelled. For this component, you can substitute the RB/A inside, and then the omega can be assumed to be this value. For this acceleration component, you need the omega dot. So omega dot AB. So we always follow the vector direction. So we shouldn't write the BA here, it should be AB. So the omega dot AB is the angular velocity for this rotation. Since it's not provided, therefore we just assume it in the positive k direction, which is in counterclockwise to the z direction. With that, you success to obtain the motion for the fixed axis rotation at root AB. So this is the velocity V. After you substitute the VA to be 0, omega AB to be the omega AB in the k direction. So this is our assumption. And then the displacement vector from A to B here is given by this. So this is the first equation that you obtain. In terms of the acceleration for the root AB, so we know that the acceleration at point A here is equal to 0. Omega naught AB is unknown, and we assume it to be here in the k direction. So we just substitute inside. RB/A is equal to this, and then you have additional acceleration component here. So omega AB is unknown, we assume it to be this, and then your RB/A is equal to this, and don't forget the bracket, so you should perform the calculation here. Let's continue to analyze the motion at root BC here. Similar to the previous analysis where you assume A is doing the translation, while B is rotate with respect to A. Using the same approach, we assume B is doing the translation now, and C is rotate with respect to B. With that, you can form the velocity and acceleration equation at point C here, which is equal to the translation component at point B here, plus the rotational component at point C with respect to B. Let's substitute the parameter to the velocity equation for root BC. The velocity at C here is equal to 2 in the x direction, therefore you can write 2i here. The velocity at B can be computed from here. Substitute the equation 1 into this, then you should obtain this parameter. Since you have the point C rotate with respect to point B here, therefore you need the displacement vector RC with respect to B here. So you can substitute inside the RC with respect to B vector here. So this is the answer. And then the rotation here is equal to omega BC. And omega BC is unknown, you assume it to be positive k direction. Therefore you have this term. So you know that I cross j give you k. By using the sacred root, k cross I will give you j. Therefore, k cross I here give you j. How about k cross j? So, I cross j equal to k. If you take k cross j, then you obtain negative I. If you don't know this trick, which is the cyclic rule, to compute this, then you use the determinant method by substitute the ijk inside, and then you have the omega bc at the k direction. So you put the omega BC here, and you have 0 value in the I and j direction. Then you cross it with the 0.4 cos 45 in the I direction. So this gives you approximate to 0.28 plus 0.4 sin 45, which is equal to 0.28 in the j direction here, and you have 0 value in the k direction. So after you perform this, you should obtain the answer in j and negative I direction as well. After you perform the calculation on the right hand side, you should obtain this answer. Then you can compare the coefficients to find the omega AB and omega BC here. For example, you compare the coefficient for I. So 2 is equal to this coefficient. And when you compare the coefficient for j, since there is nothing on the left hand side, so you have 0j. So 0 is equal to this term. Therefore, we can rewrite this to be 2 equal to this coefficient, and then this coefficient is equal to 0. So you have two equations and two unknowns. Therefore, you can solve the equation simultaneously to obtain this answer. And you obtain the omega AB to be negative 2.44 and omega BC to be negative 2.59. Initially, you assume that the omega AB and omega BC here is rotated in counterclockwise, which has the vector in the positive k direction. So now you obtain this value, you can substitute inside, and you see the direction is in negative k direction. Therefore, you should change the direction of rotation in this way, and this is the actual angular velocity direction. There is a correction here. Omega AB should be negative 2.44 instead of negative 2.59 here. So please correct this. So the omega BC here, initially we assume it to be counterclockwise. So after you substitute this value inside, you obtain negative 59k. So the direction for the omega BC is in negative k direction, which is clockwise. Therefore, we need to change this to the clockwise direction. In the previous example, you success to obtain the angular velocity at the root AB and root BC here. So we can substitute the parameter omega AB inside this equation by calculating the acceleration component here using this parameter. Then you can obtain the acceleration B equal to this answer. This is the acceleration equation obtained from the root BC. You can obtain the acceleration B from here, substitute the RC with respect to B here, and also the omega BC from here. After perform the calculation, you should obtain this equation. By comparing the coefficient for the I, you can compare the coefficient for the J on both sides. Then you should be able to form two equations. First equation is negative 10 equal to this coefficient. Second equation is 0 equal to this coefficient. By solving these two equations simultaneously, you should obtain the unknown omega dot AB and omega dot BC to be this answer. Since you have the positive value for the angular acceleration, therefore we know that they are rotated in the counterclockwise. By substitute the omega dot AB into this equation, then you can obtain the acceleration at point B. Forget to mention, if you substitute the omega AB that you obtained previously to the velocity equation here, then you can find the velocity at point B as well.